Chapter 10 Validation. Lambda CDM had an entire century to measure and catalog the universe. The paradigm managed to turn failed predictions into successes through systematic retrofitting. The CMB was discovered accidentally as a radio inference, then claimed as a prediction despite wildly incorrect temperature estimates ranging from 5 Kelvin to 50 Kelvin. Dark matter was invented to explain unexpected galactic rotational curves. Dark energy was introduced when supernova showed acceleration instead of expected deceleration. Each observational surprise that should have falsified the expansion paradigm has been added as a new adjustable parameter. Alternative frameworks are in an unusual predicament here. Lambda CDM has already claimed explanatory territory for virtually every cosmological observation through post hoc accommodations. How can any alternative compete with an ever-changing and adaptable paradigm? The proposals in this book are not portions of a new theory. They are corrections based on the fundamentals of general relativity. General covariance does most of the heavy lifting for us, as it requires us to treat mass density as scale-dependent. The proposed distribution, gravitational redshift, the CMB temperature, rising curves, and the horizon are all consequences of that scale dependence. Because general relativity already provides us with a simple mechanism to redshift light, and expansion is a theoretical phenomenon, the proposed framework should be considered the default cosmological solution. The mistake that science made was the assumption of homogeneity, which makes Einstein's universe appear to collapse. The addition of the cosmological constant was unnecessary because collapse is what you would want for that particular gauge. It is physically impossible for the universe to have the same mass density at all scales, but it would absolutely collapse if that were somehow the case. Consider for a moment that we are attempting to formulate a solution based on the light coming from a distant star. The only information available to us is the emitted and observed frequencies. The change in frequency is sufficient to formulate a solution to the Einstein field equations, but light can only encode the geometry as a scalar constraint. Whatever solution we formulate from it may not be accurate. The same redshift could arise from either static gravitational fields or a dynamic space-time expansion. Fortunately, it's a big universe to sample from. Now consider that we take a large sample of stars from various locations and redshift ranges. We then use this information to formulate all possible solutions that fit the observational constraints, deliberately excluding cosmological solutions that invoke additional theories like expansion. The idea is to see if we can have a proper accounting of all starlight without ad hoc theories. We can apply this thought experiment directly to real-life observations. Suppose we use the formulation from Chapter 4. In that case, we end up with a complete account of the cosmological redshift, a full account for the horizon, and a full account of the CMB temperature, all from using a single geometrical framework. Essentially, all we did was assume the universe was not expanding. If the universe were expanding or contracting, this convergence would break down. The horizon scale would not match the Hubble distance, the Hawking temperature would require different emission physics, and the precise CMB temperature of 2.725 Kelvin could not emerge naturally from the same geometric parameters that explain redshift observations. Someone once told me that my framework does not outright falsify expansion, but instead leaves room for a tiny amount of expansion or collapse. And I think he was right. If the CMB temperature and the redshift don't align perfectly, then it is still possible for the universe to be expanding or collapsing. However, one should be exceptionally careful with this avenue because it is very doubtful. For one, a collapsing universe would have a preferred frame of reference, meaning it would be collapsing toward a single point. In addition, detecting the collapse would be difficult unless you are near the point of collapse. The likelihood of you being in a location is presumably 1 over infinity. And sure, something could make mass repel in a way that makes it appear as though space-time is expanding, but at this point, there is no evidence to suggest this is the case. Predictions. In the previous chapters, we constructed a consistent cosmological model by removing assumptions and eliminating magical theories. Numerous tests and predictions can be used to validate the model, though I am hesitant to make exact predictions. If I'm right, it means that virtually every cosmological observation in the last 100 years has been misinterpreted by academia. These failures show a lack of curiosity and discipline within the fields. Such incidents often occur in bureaucracies that have an intolerance for criticism. New ideas and proposals are usually viewed as crackpottery unless the authors are already established as knights of the orthodoxy. And if that is the case, those ideas are published regardless of their relevance to physical reality. Laziness abounds. Mistakes are also common, especially in physics, but that is expected. Fraud, on the other hand, should be nearly non-existent in scientific publishing, and yet it's so common that it's frightening. One study analyzed 21 surveys, 18 of which were included in the meta-analysis, conducted in the mid-1980s to 2005, primarily among researchers in the US and UK. They found 1.97% of scientists admitted to committing serious misconduct at least once. 33% admitted to questionable behaviors, and 14% reported having heard of colleagues falsifying data. However, perhaps the most concerning tidbit was that 72 of the respondents reported witnessing colleagues engaging in questionable practices. Of course, none of this should impact my ability to make predictions within this model. But it absolutely means that all published interpretations of scientific data should be viewed through a skeptical lens. The incentives to tell the truth about the data are not aligned with the goals of publishers and reviewers. The potential for mistakes in complex fields like cosmology is already high, even among honest researchers. The particular model outlined in this book, while simple and elegant, has a high chance of being misunderstood. Lambda cosmology has completely ruined most of physicists. It is common for professors to claim that expansion is a prediction made by general relativity, which is an outright lie. I've had week-long debates with astronomers who believe the mass density of the universe remains constant on all scales beyond a certain point. With all of that said, there are studies that could be conducted to distinguish the proposed model from Lambda CDM. The most apparent difference between the two is that objects in Lambda CDM should recede away from us over time, which in turn would lead to a slight increase in the observed redshift. If caused by gravity, the redshift would remain relatively fixed over time. But this isn't necessarily true, as massive objects tend to attract additional mass and grow with time. Any class of object could be in a growth stage, which means that care must be taken in selecting the objects for the sample. Several projects are already in place or planned for the future that will help distinguish between the two models. SHUES, Supernova Hubble Constant for the Equation of State, is one such program that might be helpful in this arena. Nobel laureate Adam Rees leads the project and already has several published papers. Now the project is using data from the JWST telescope, which will eventually provide more conclusive evidence against Lambda CDM. Modeling, observing, and making predictions about events that happened billions of light years from Earth is difficult to say the least. While we should not put too much stock in any scientific paradigm, there is obviously a hierarchy to the trustworthiness of theories, and cosmology is weak sauce compared to the laws of thermodynamics and plate tectonics. Cosmology's weakness comes from its metaphors and conclusions about large-scale evolution. Making accurate predictions in the field is certainly feasible and commonplace. Lambda CDM's predictions come from having a proper accounting method of the physical phenomenon being observed, including redshift, CMB, and the BAO. However, each of these predictions comes along with caveats, and there is also an underlying issue with how to assign success. The core problem is that claims about success are being attached to the entire Big Bang package, but that isn't the case with any single prediction. Lambda CDM's predictions depend on a stack of assumptions about initial conditions, thermal history, how atoms formed, distance measurements, and how things evolved over time. When this entire stack gets treated as a single theory, it becomes impossible to tell which parts are actually doing the work. The language then shifts from "this combination fits the data" to "the entire model is true." The history of the atomic model shows us why we should be careful about attributing success to a paradigm, given a specific prediction it made. Atoms started as indivisible spheres. After discovering the electron, J.J. Thomson proposed that atoms were spheres of positive charge with electrons embedded like plums in pudding. Soon after, Ernest Rutherford proposed electrons orbited the nucleus like planets around the sun. This model had a fatal flaw. Classical physics predicted the electrons would fall out of orbit and spiral into the nucleus while radiating energy. Despite the model having an irredeemable error, Rutherford was still able to make several successful predictions, including the correct scale of the nucleus and the atom. What survives from the old models may not be pictures scientists had in their heads, but the mathematical relationships that actually made successful predictions.